now that we have kind of an idea of this idea of spontaneous processes and reversible and irreversible processes, we're going to focus a little bit on entropy and how it applies, or how it talks about the second law of thermodynamics. Our explanation of entropy so far has been, somewhat simplistic, where we just look at it as the entropy being the randomness of our system, the things that make up our system. One of the things we want to realize is that entropy really deals with the extent to which the energy in a system can be distributed among different motions in the molecules of the system. And so we'll get into that in the next section, I believe, where we'll look at what does it mean for randomness to exist in terms of how that energy can affect that substance. All right, for now let's take a look at how do we determine entropy. Well, there's similar to enthalpy, where we had the difference between our initial and final states. For the enthalpy, we have the same thing for entropy. So the change in the entropy is equal to the final entropy minus the initial entropy. So for a process that's occurring at a constant temperature, and this term isothermal is kind of an important idea. I'm not sure if we had talked about that before, but isothermal means that it's happening at the same temperature. The change in entropy is equal to the heat that would be transferred if the process were reversible, divided by the temperature. So this goes back to the people that were studying the combustion engines in the 1800s, and when they came up with this idea here, that change in entropy is equal to the heat that's transferred in a reversible process divided by the temperature. And remember that we're talking about isothermal systems, so T is constant here. Now, what if we also have where we're dealing with a constant pressure? Well, if we have a constant pressure, remember that Q is equal to delta H. If we substitute that into our equation, then we have that our change in entropy can be equated to the delta H of the process divided by the temperature. So we can look at a phase change then, this. If we look at the heat of fusion of water, so we're going to change water solid to water liquid, and the delta H for this process is equal to 6,000 joules per mole. We can say that the delta S is equal to the delta H, so that would be 6,000 joules per mole divided by the temperature. So the temperature at which this is a reversible process would be at 0 degrees Celsius. And that's where you can go back and forth with just that infinitesimal change. So 0 Celsius would be 273 Kelvin. And just a reminder, we do need to be careful about our temperatures. We need to make sure that we're using the Kelvin temperature, the absolute scale here, which means that the delta S for this process is 22 joules per kmol. Now let's take a look at the entropy change of the surroundings, perhaps, in this process. So this would be the change in the entropy of the ice cube. If we were to put that ice cube into your hand, so just kind of keep that in mind there. So if we melt the ice in your hand, which let's imagine is about 35 degrees Celsius. The change in entropy of your hand then, so obviously the energy from the ice is going to go into your hand. So we've got, if the ice absorbed 6,000 joules, your hand must have gained, or your hand must have lost 6,000 joules of energy. And your hand then is at a different temperature. It's at 35 degrees Celsius, which would be 308 degrees Kelvin. So in this case, the entropy change is negative 19.5 joules per K degrees Kelvin. Okay. So the first thing you want to realize is that unlike the first law of thermodynamics, where energy has to be conserved, entropy is not conserved. As a matter of fact, this brings up an important idea, which is if we look at the delta S of the system plus the delta S of the surroundings, that's equal to the delta S of the universe. Okay, and so again, thinking about this in terms of energy, normally the sum of the energies, the change in energies, should be 0. Delta S of the universe is not going to be equal to 0 in a process, in a spontaneous process, I should say. However, if we look at in this case, if we do the delta S of our universe, we have 22 joules per K plus negative 19 joules per K. We know this that the entropy of the universe went up. Let's see, so 19.5. The delta S of the universe went up by 2.5 joules per degree Kelvin. So the delta S of the universe went up. Now, this is true of any spontaneous process then. Any irreversible spontaneous process, by definition, the entropy of the universe will increase. And that's that's the second law of thermodynamics, which I believe we have on the next slide. Yeah, so for any spontaneous irreversible process, the delta S of the universe has to increase. For any reversible process that's at equilibrium, or for any reversible process, that would mean that the entropy of the universe would have to be 0. So the second law of thermodynamics states that the entropy of the universe increases for spontaneous processes, and the entropy of the universe does not change for reversible processes. So if we think back to our rusting nail, the rusting of the nail is going to be an increase in entropy for the system. So the system is going to increase in randomness. Oh, excuse me. The rusting of the nail will cause a decrease in the randomness because you're putting things together. Anytime you put things together, that's going to decrease the randomness and decrease the entropy. So if the rusting nail is decreasing the entropy of the system, what must be happening to the entropy of the surroundings or the universe? So kind of think a little bit about that. So what this means then is that we can to look at whether a process is going to be spontaneous or not, we can actually in a sense look at just the entropy. If the overall entropy of both the system and the surroundings increases, that means that the entropy of the universe increases, which means that that's a spontaneous process. So now we'll take a look at, from the molecular point of view, what's happening to increase the entropy of things, or how is energy being used to change the different modes of motion of particles.